Welcome back. Now the demo I'm going to do, it's an actual problem that we do also in the class. I have a beam of light coming in like this. I have a slab of glass. I can draw the outline of that slab of glass like this. At a certain angle, I'll turn off the lights here so you can see a little bit more detail how the beam of light is bending. And then we're going to be asking if the original separation distance of these lines is a certain value, what's going to be the separation distance of the lines after these two lines have gone through the glass slab and come out. The separation distance is going to be changing. So if I turn off the light, you can see this. Okay, so you can see here the left two beams of light come. I'm going to draw their outline like this. The left two beams of light come, they bend inward and then they bend outward when going out, okay? And then the middle one also comes in, goes through the glass, bends inward and then bends outward, right? But the one on the far right, the beam of light comes in and just goes through the air without bending at all, okay? So I drew those lines. Now I can turn the lights back on. Okay, so now you can see what happened was the left two beams of light came and then they bent inward and then they bent outward. So the distance here, this distance and this distance doesn't change, right? Because they bend in together and then they go back out. These two distances d, which is the same as this distance, but then eventually this one d prime gets larger. So we want to be able to predict what d prime is. What's the distance between these two because they get larger, then compare that to the theory, right? So let's measure that right now. Okay, I'm going to get my vernier. Okay. That's about, let me measure my d prime, the experimental d prime, right? So that's going to be this distance, centimeters. Okay, what else do I need to know? In order to calculate the theoretical d prime, I need the angle that's coming in, and I need the thickness of the slab, right? So let me take this out, the slab. All I need is this thickness of the slab, the up and down thickness. So let me measure that. 0.5 centimeters, and I need the angle that's coming in, the original angle. So I could put my protractor here. That's 57 degrees. 57 degrees from the plane of the mirror. 57, right? But to use Snell's law, we need this angle, right? From the normal line, right? So from the normal line, what would that be? 33 degrees, right? 33 degrees. So then I can apply Snell's law. The n of the incident medium, sine of the incident angle is equal to n of the refracted sine of the refracted angle, right? So the incident medium is air in this case, so that would be 1. Sine of 33 is equal to the index of refraction of the glass medium, so I'm assuming it's crown glass, or it could be some other material. We would have to know the specific index of refraction of that material. Then we would do sine of theta r, right? And then you get 21 degrees pretty much. Theta refracted 21 degrees. So what does that mean? That means this one will bend inward such that this is 21 degrees, right? And then it's going to bend outward again back to the 33 degrees, right? So this one, when it comes out, that's why when these two beams of light come out, they're parallel to the original beam of light that was never bent. So they should come out parallel. So they bend inward 21 degrees, and then they bend outward back to 33 degrees. So it's just a reverse process. Refraction inward, refraction outward. But then what happens, because they had bent inward, they're going to be at a greater distance from the original distance. So how do we find that distance? Okay, so now let's find out what this distance is from here to here. Okay, from the normal line all the way to where it's coming out. Now, since we know the thickness is T, how are we going to do that? Okay, so the triangle looks like this, right? This beam, then it goes like this, and this is the thickness T, and this is 21 degrees, right? So that means, what is this distance? We can say tangent of 21, right, is equal to this distance x. So I'm going to put this distance here, x, from here to here. Okay, so tangent of 21 is equal to x over t, and then my t was 6.5 centimeters, right? So x is equal to 6.5 tangent of 21. Okay, so 2.495, or very close to 2.5 centimeters. So that would be the distance from here to here. Now we can ask the question, what would that distance have been if this beam of light did not bend at all? Okay, so if this beam of light, imagine, had gone through straight, okay, and gone through the slab, right? What would that distance be? X prime. Okay, so then we can say here, and then we could put here T, that if there was no glass, that angle would have been 33 degrees, right? So that would have been 33. So we can say tangent of 33 is equal to x prime over t. So x prime would have been what? 6.5 times tangent of 33, right? Okay. Okay. So that represents this whole distance. Okay, now we can say the distance between the two, right? The distance between the two beams of light, distance is 3.75, right? So that would have been that distance there. Okay, now what are we trying to solve for? We're trying to solve for, let me write this one over here. This is 3.75. We're trying to solve for this distance. The new distance between, when this beam of light comes out, this distance between the two beams of light. So if this is 3.75, and how can I calculate this distance? Okay, well, what I need to do, because the distance between here and here is 3.75, I need a way to calculate this distance. Okay, so now focus yourself on this little triangle, on this one which I'm going to color. Okay, like that. So let's focus on that, like this. So now if I subtract x prime minus x, that gives me this bottom base distance, right? So 4.22 minus 2.5, that's going to be what? 1.72 centimeters. So what my goal is to find this piece like here. So this piece here, let's call that one y. Okay. So if I add that piece to the 3.75, that's going to give me my experimental d prime. Okay, so what is that distance? Okay, well, if this one is coming at an angle of 33, right? This one here. So it's basically, that means it's hitting, this beam of light is coming this way, right? That represents this blue beam of light. So it made this angle was 33 degrees, right? That means this one is 33. The angle that it makes with respect to the normal, this is 33. This is 33, and then so this is a 90-degree angle. I can subtract 33 from 90, right? I can get 90 minus 33, and that's going to give me my original angle, which I had measured, which was 57, right? 57 degrees. So then I can say, this is the hypotenuse of the triangle, so I can say sine of 57, okay, is equal to opposite over hypotenuse, y over 1.72. That will tell me what the y is, right? The extra piece here, y, which I'm calling y. Now add that to 3.75. Add that to 3.75. You get 5.19. Okay? D prime is equal to 5.19. This is the theoretical centimeters. Okay? So now if I measure that, so if I measure this d prime again, just to be more accurate, okay, 5.14 centimeters. Okay, pretty close to the theoretical. So my percent error is going to be very good. Percent error, 100% times 5.19 minus 5.14 over 5.14. So the measurement wasn't very accurate because the marker is so thick and I wasn't using a ruler, so I was a bit crooked. So I had to go back and look at the beam itself and look at the beam that was coming out, and then I corrected my reading, so I got a better result. So if you do this with a pencil, very sharp pencil, and do it on a piece of paper really nicely, you can make this result almost like down to less than 1% error. So my percent error is going to be, okay, so now you can see how to do a problem like this where you're testing out Snell's law, but you're also testing out to see if the lines coming out are parallel, and if the distances gotten bigger, you can do some calculations to predict what that new distance is, and then using all the geometry of refraction and stuff and the Snell's law, you can get a result and you can compare it with the experimental result. Okay, thank you very much.